Define design requirements. Before starting the design, it is essential to clarify the specific requirements of the product. This includes the product's functions, intended uses, operating environments, appearance requirements, and possible regulatory and standard requirements. For example, for automotive interior plastic parts, factors such as wear, resistance, chemical, corrosion resistance, and compatibility with other vehicle components need to be considered. At the same time, ergonomic factors should also be taken into account to ensure that the parts are comfortable and safe to use. According to statistics in the automotive industry, the rework rate of products due to unclear design requirements can be as high as 15%. Select appropriate plastic materials. The selection of plastic materials has a decisive impact on the performance and cost of the parts. Different types of plastics have different properties, such as strength, toughness, heat, resistance, and chemical resistance. For example, polycarbonate (PC) has good transparency and impact, resistance properties, and is often used in the manufacture of spectacle lenses and automotive headlight covers, while polypropylene (PP) has good chemical, resistance, and fatigue resistance properties and is widely used in food packaging and injection molded containers. When selecting materials, the cost, processability, and environmental requirements of the materials also need to be considered. Generally speaking, general purpose plastics such as polyethylene (PE) and polypropylene (PP) have lower costs, while engineering plastics such as polyamide (PA) and polyoxymethylene (POM) have higher costs but better performance. Conduct product styling design. Product styling design should not only meet functional requirements but also consider aesthetics and market demand. Designers need to use 3D modeling software such as CAD, Pro E, etc. to create a virtual model of the product. During the styling design process, attention should be paid to the wall thickness uniformity of the parts. Generally speaking, the wall thickness of plastic parts should be controlled between 1 to 3 millimeters to ensure good molding quality and avoid defects such as sink marks. For example, in the design of a mobile phone case, in addition to considering its compatibility with the internal components of the mobile phone, an appearance that conforms to consumers' aesthetics and grip habits should also be designed. Through market research, it is found that simple and smooth appearance designs are more popular among consumers. Mold structure design. Mold structure design is a key link in the design of plastic molded parts. It includes the selection of the parting surface, the design of the cavity and core, the design of the gating system, and the design of the cooling system. The selection of the parting surface should consider the ease of part demolding and the molding quality, and generally it should be selected at the largest outline of the part. The design of the gating system should ensure that the plastic melt can fill the cavity evenly and quickly, and the size and position of the gate have a great impact on the molding quality. For example, in the mold design of a large scale plastic box, the gate diameter may need to be designed to be 5 to 8 millimeters to ensure the smooth filling of the melt. The design of the cooling system should ensure that the mold can be cooled quickly and evenly, and usually the diameter of the cooling pipes is 8 to 12 millimeters. Conduct mold strength calculation. The mold needs to withstand high pressure and high temperature during the molding process, so strength calculation must be carried out to ensure the reliability and service life of the mold. Strength calculation includes the strength and stiffness calculation of components such as the cavity, core, and mold plate. For example, for a mold cavity that withstands high pressure, it is necessary to calculate its stress and deformation through mechanical formulas according to the injection pressure of the plastic material used, generally between 50 to 150 megapascals, and the size of the cavity. If the calculation results do not meet the strength requirements, the mold structure needs to be optimized, such as increasing the wall thickness or adding ribs. Manufacture and debug the mold. After completing the mold design, the mold needs to be manufactured. The manufacturing process includes machining, electrical discharge machining, heat treatment, and other processes. After manufacturing, the mold needs to be debugged, and the molding quality of the mold and the dimensional accuracy of the parts are checked through trial molding. During the trial molding process, some problems may be found, such as flash, sink marks, and dimensional deviations of the parts, and the mold needs to be adjusted and optimized. According to experience, generally, the mold needs to go through 3 to 5 trial moldings to achieve the ideal molding effect. After the product is put into production, it is also necessary to continuously improve and optimize the plastic, molded parts, and the mold according to the feedback during the production process and market demand. For example, by improving the cooling system of the mold, the production efficiency can be improved. According to the new requirements of the market for the product appearance, the product styling can be optimized. Continuous improvement and optimization can continuously improve the quality and competitiveness of the product.